Okay, well, thank you for having me again speak to the chapter. This presentation is on Needs and Requirements Manual, Section 6, Design Input Requirement Definition, and Section 7, the Design Input Requirement Verification Validation. Last year in April, I gave a presentation on Section 4 and 5, which had to do with lifecycle concept and needs definition. And so this presentation, I'm going to do a fire hose view of Section 6. There's a lot of material. For all the details, get a copy of the Needs and Requirements Manual, and you can do a deep dive into any of the particular topics. There's a lot of detail in the Needs and Requirements Manual, but the guide to Needs and Requirements is a Cliff Notes version. And so it has a section on defining design input requirement definition that is much shorter than what this section is. And so what people would want to use our products is you go to the guide to Needs and Requirements first, and then if you want more elaboration, more detailed knowledge, then you can look that topic up in the Needs and Requirements Manual. The Needs and Requirements Manual that's available in the INCOSE store is the May 2022 version. The content of this lines with and expands INCOSE SE Handbook version 5 material. I said version 5, which hasn't came out yet, but for the sections dealing with requirements, I and Mike Ryan are the authors of those sections. And each of those sections refer to our products, the Needs and Requirements Manual, the Guide to Writing Requirements, and the Guide to Needs and Requirements, the Guide to Verification Validation. So they elaborate on what's in the SE Handbook. And Wiley has approached INCOSE, and INCOSE signed a contract with them for version 2 to be published by Wiley sometime in 2024. So that's something to look forward to. So we have a set of products, the Guide to Needs and Requirements, the Guide to Writing Requirements, and the Guide to Verification Validation. Notice the Guide to Writing Requirements, I have 1 July 2023 date on that. We are updating that to a version 4, and we're in the last review cycle of that. And so any of the INCOSE members should have saw some announcement on the Yammer page about that. And if you have time, we really would like you to read through that and give us any last comments. And then we'll incorporate those soon at Tech Ops. And the goal is for it to be released at IS at the same time the System Engineering Handbook version 5 is released. The Requirement Working Group awarded at IW 2023 the product of the year for all of our products. So that was a great honor for us. So the Needs and Requirements Manual, like I said, supplements, elaborates on the INCOSE SE Handbook version 5, provides more detailed guidance on the what, how, why concerning needs and requirements definition and management, verification and validation, definition management across the lifecycle. Addresses ambiguity and inconsistencies in non-ontology concerning needs and requirements, definition management, verification, validation. So when you go through the Needs and Requirements Manual, you'll see some new terminology. It's not really new. It's pulled from different groups. We make a big differentiation between needs and requirements. And we talk about an integrated set of needs. And then we talk about design input requirements. And that phrase was borrowed from the medical device industry. To successfully complete system verification, system validation, the needs and requirements for the system, as well as system verification, system validation artifacts must be managed throughout the entire system lifecycle. The Needs and Requirements Manual provides practical guidance on the activities required to achieve those outcomes. Needs, requirements, verification, validation are the common threads that tie all lifecycle activities and processes together. There's 16 sections within the Needs and Requirements Manual. This presentation, we're focusing on section 6 and 7. One of the big things that we talk about is that validation, verification are continuous activities across the life cycle. This is one of the charts that's been very popular. I've heard some people printing this out as a poster, putting on the walls in their organization to make sure that people understand the differences in what we talk about verification, validation. But the focus of this presentation, again, is on going from the integrated set of needs into sets of design input requirements. Section 6 has a bunch of different topics that it covers. One thing it doesn't talk about is how to write a well-formed requirement. That's the Guide to Writing Requirements. So in this presentation, I'm not going to be talking about writing of well-formed requirements. However, the characteristics that's defined in the Guide to Writing Requirements for well-formed individual requirements and sets of requirements are equally dependent upon the activities, the analysis that goes into defining the requirements, as it is to adhering to the rules for writing well-formed requirement statement. In the past, a lot of organizations focused on how to write well-formed requirements, not realizing that a lot of the characteristics come from that underlying analysis that takes place. And so one of my other sayings is that defining requirements is not an exercise in writing, it's an exercise in engineering. So when we talk about Section 6, the design input requirement definition, the focus is on design input requirement definition activities and transforming the baseline integrated set of needs into unique quantitative and measurable sets of design input requirements expressed as shelf statements. And so that's shown here in the red circle. These design input requirements are inputs for defining the system architecture, flowing requirements down, allocating from one level of the architecture to the next, and inputs into the design process. And so I think it's really appropriate that we call those design inputs. By design inputs, that implies that in our sets of design inputs, we don't want any design output kind of stuff. One thing to differentiate is that the focus is on the what, not the how. And so saying design input really makes it clear to people that you're not putting design solutions in the set of design input requirements. Another thing from the Needs and Requirements Manual that we stress is that even though we have this section on design input requirements definition, system engineering is an iterative and recursive process, and a lot of the technical processes are intended to be done concurrently. And so even while we're doing the upfront processes of lifecycle concept analysis, maturation, needs analysis, definition, we're doing modeling. We're also starting to look at what the requirements are going to be, in addition to what the needs are going to be. So a lot of concurrent activities are intended. And so that given that we have this iterative and recursive nature of system engineering, everything that we're talking about can be applied to your system of interest, whether it's the system, subsystem, system element, set of design input requirements, no matter the architecture level. And it's important to understand that the information-based needs and requirements development management approach defined in Section 3 and the lifecycle concept needs definition activities discussed in Section 4, that the result of completing these activities, not only an integrated set of needs, but also underlying analysis and associated artifacts from which they were formed. And as part of these activities, the project team will have been concurrently defining, like I said, a preliminary draft set of design input requirements. Following this concurrent approach, then the design input requirements definition activities will build upon the work that was done previously, resulting in mature, well-formed set of design input requirements. Using this concurrent approach is really preferred. There's going to be some issues that may come up when defining your design input requirements. And so when they come up, we can address those in a less formal, agile manner early in the life cycle during the lifecycle concept analysis and maturation activities and resolve those issues rather than in an old waterfall approach that a lot of people are familiar with. An IPO diagram for this section, and the manual has an IPO diagram for each of the sections showing what the inputs are, what the activities are, enablers, and then what the outputs of this. And so there's a lot of inputs into this. I won't go through all of them in detail. A lot of enablers that we have to deal with that really enable us to do these activities. And then we'll go through each of the activities. And the result of this is a whole lot of information. It's not just a set of requirements or sets of requirements for the whole architecture. So we have to think in more holistic view of what we're doing and not just think about we're developing a requirements document. We're doing so much more as part of this process. So there's a lot of work involved if we're going to really do it right. These are the activities in Section 6. We start with the integrated set of needs. We have to plan for how we're going to do our design input requirement definition activities. First thing we're doing is we're transforming the integrated set of needs into our design input requirements. As part of this, though, we have to establish traceability. We have to assess the interactions, interfaces, define interface requirements. There's attributes I'm going to talk about that we're going to record for each of the requirements. We're going to plan ahead for system verification as we write each requirement. Then we're going to finalize our set of design input requirements. verify and validate the set of design input requirements. So we're going to verify that they're written properly per the rules for writing good requirements, validate that they actually communicate properly the intent of the needs or the parents they were transformed from. Then we baseline the design input requirements. Then we're going to manage those. And section 14 of the manual goes a lot of detail about managing. But then, depending where we are in the architecture, we may have to flow the requirements down to the next level of architecture through allocation and budgeting. And so once we've done that, then for each of the receiving subsets and system elements, then they're going to start this process over again and do the lifecycle and needs definition activities, and then they'll write their own set of design input requirements for their particular entity. If we have no further elaboration, then we're handing this over to architecture and design and then production. There's a question, do I have a SysML diagram for slide 13? The answer is no. I've tried to keep all the manual tool agnostic, and so I don't have any SysML included in the manual. So 621 is the transforming needs in design input requirements. So the integrated set of needs come from a whole lot of different sources. And the integrated set of needs is not what people think of as stakeholder needs and requirements. The integrated set of needs is a result of a whole lot of work and needs analysis. They're well formed. The guide to writing requirements really should be titled Guide to Writing Needs and Requirements, because it addresses crafting the needs and sets of needs just as much as it does requirements and sets of requirements. And the integrated set of needs are transformed into the design input requirements. But because we've done all this upfront analysis to define the lifecycle concepts, the integrated set of needs, then it's going to be a lot easier to define the actual requirements. And also the quality of our design input requirements then is going to depend upon the quality of our integrated set of needs. If the integrated set of needs is incomplete, inconsistent, not correct, not feasible, then the resulting design input requirements are not going to be either. So when we talk about needs and requirements, and this is something that's new to a lot of people, in our vocabulary, we all talk about needs, but they're kind of a pink elephant in the room. They're really not well documented. They're not configuration controlled in the manner that we're talking about in our products. But it's important that we understand the different perspectives. So the needs represent the stakeholder, customer, acquirer, user view of the system. What do the stakeholders need the system to do that result in their problem to be solved or opportunity to be realized within the defined constraint with acceptable risk? It communicates stakeholder expectations for the end state once the system's delivered. In the end, what's going to make our customers happy. And the agreed to baseline set of requirements represents the scope of the project. And that's important because when the scope is baseline and the customer signs off on it, they're agreeing to provide the budget and the resources necessarily to implement that scope. And so when we have needs dealing with security or sustainability or safety or resilience, then the customer's saying, I'm willing to pay for those things to be realized within the delivered system. And in that respect, then the system is going to be validated against the integrated set of needs. The requirements represent the technical developer view of the system, so a different perspective. What must the realized system do in order to meet the needs? The needs are transformed into design input requirements that result in a design that, when realized, will meet the needs, and the system will verify it against this design input requirements. So this is a different view of that same thing. The stakeholders are asking, what do we need to do when using the system? What do we need the system to do? What quality do we need the system to have? What do we need the system to comply with? Regulations and standard. What external systems do we need the system to interact with? So those are all questions the stakeholders have up front. So we have to work with stakeholders, understand all these questions. There's going to be disconnects and problems, inconsistencies, and so on. So then we do a lifecycle concept analysis and maturation to come up with at least one feasible set of concepts that will address these needs. And then we baseline those. And then in the transformation of the needs into requirements, then the developers or whoever's responsible to develop a design input set of requirements, they're asking the question, what must the system do to meet the needs? So a whole different perspective that we have, and both are very important. It's really hard to develop a good set of requirements if you really don't have a good handle on the needs that you're going to transform those from. This is one method that we can use column ABC. So we list our needs. I have them here organized as functional performance, a function part. Some people think form, fit, and function. And so the form, function part, and then operational is a fit, a lot of the interactions with external systems, enabling functions, if you will, and then the physical characteristics, the form. And then we have the quality, the abilities, and then standards and regulations. We have to talk about how we're going to show compliance. And the project team is going to do the requirement analysis to transform the integrated set of needs into a set of design input requirements, asking what must the system of interest do to fulfill each of the needs. The answers to those questions would be one or more design input requirements that are necessary and sufficient to meet the parent need. So in column B, when we ask the question, then we can start writing the requirements. And then if that requirement involves interaction with some other entity, then we're going to start filling out column C with the external entities and what the interactions are to make sure that we cover all the interfaces. And this needs and requirements matrix is one tool that people find useful for doing that transformation of the needs into the design input requirements. Organizations need to define a template for how they're going to organize and manage their requirements. In a document-centric world, there's the historic documents that people use with various names, and they have outlines for those documents. And the needs and requirements manual is focused on data-centric world. So we don't mention any of the classical document names. We're talking about sets of requirements for an entity that we're talking about. A lot of the old historical requirement documents are really a cause for a lot of the issues we have, because they have a mix of different kinds of things in there. Not all of them are really design input requirements. Some organizations define the contents differently, even though they use the same name. We try to avoid all that by just never talking about a document name. We're assuming in all this that everyone's going to go to a data-centric practice, which I feel is the real intent of MBSE. So all of our requirements are going to be managed within an integrated database. So, but organizations need to define that, how they're going to manage and organize the sets of design input requirements. And I say sets because remember, it's not just one set of design input requirements. It's a system level, subsystem level, system element level, and I'll get into that a little bit more, but there's going to be multiple sets that define our system. Considerations for each type of requirement is in 6.2.1.2. And so it goes, there's a section on functional performance, operational, form, quality, and compliance, giving some considerations that you should have when you're doing the transformation for each one of those, and some guidelines for formulating the design input requirements. One thing that people need to consider is tolerances and ranges, accuracy and precision. It doesn't really good to have an accuracy requirement and not a precision requirement. And then both of those really have to do with measurements. I've had people say you have to transmit something with a certain accuracy and precision, but that doesn't really compute because accuracy and precision is really about measurements. And then something that a lot of people fail to think about is system lifetime and expected performance. So when you define a particular performance value, are you talking about beginning of life or end of life? And I know the software people don't really have to consider this a lot, but when you're dealing with hardware, software, combined systems, hardware wears out. And there's a degradation in performance in hardware systems. And so we have to be thinking ahead about that. This section goes into more detail on that. And a big thing, it's important that we talk about appropriate to level. That's one of the key characteristics that are defined in the guide to writing requirements. But we want to make sure that requirements are defined for entities at the appropriate level. So when we're writing requirements for a given entity at a given level, all those requirements should apply strictly to that entity at that level. And they should not apply to any upper or lower level entities, sets of requirements. And then managing unknowns. There's going to be times when we first start writing requirements, there's going to be some to be determined, to be resolved kind of things, especially for specific numbers. And so we have a section that talks about managing the unknowns. Some people call it TBX management, but it's an important part of our requirement definition and management activities. Section 2.2 goes into a lot of detail on traceability, individual sets of lifecycle concepts, integrated set of needs, design input requirements, design output specifications, system validation artifacts, system verification artifacts do not exist in isolation. And that's one of the problems in a document-centric world is things seem to be documented in certain documents, and it's really hard to keep them consistent or to link that information together in any meaningful way. In a data-centric world, all those relationships form a three-dimensional spider web of relationships representing the data and information model of an integrated system. And so these relationships are documented via links that allow the relationships to be traced between the entities that are linked both vertically across levels, horizontally across the lifecycle. So when we talk about different types of traceability, we have the classical parent-child traceability. We also have trace to source. When we're doing allocation, I'll go into that in more detail, but there's the allocated parent requirement. We're tracing to all the receiving entities that receive that requirement. And allocation is not linking a requirement to a requirement. Allocation is linking a requirement to part of the architecture. And then you have peer-to-peer dependencies that we have to deal with. And when there is a peer-to-peer dependency, we want to make sure that that dependency is captured through a link. So if one changes, then we can assess whether the other needs to change. Interface definitions, we have traceability between interface requirements through two different systems interacting. We want to have traceability to a common definition. We want to trace our requirements to the implementing design. We want to trace to the system verification artifacts. We want to trace to the system validation artifacts and the different entities within the model. So the traceability relationship model, projects need to decide how they're going to manage traceability within a tool or a set of tools at the beginning of the project. And then once they've established this within the tools will help enforce as you're entering information that you do establish the proper links between the information. And this is, again, a big problem in a document-centric world where everything's managed in documents. It's really hard to link all this information together and keep it consistent. So you really don't have an authoritative source of truth really in a document-centric world. In a data-centric world, then everything's electronically managed, allowing you to establish these relationships within the tool set, which is really important when it comes to like change management. So if a change occurs anywhere in this matrix, you can see what the impacts of that change is on anything else that is traced to that particular entity. So the first step is selecting your tool set. When I talk about tool set, I'm talking about a requirement management tool, a tool maybe to manage verification validation, a risk management tool, a modeling tool, a tool where you're going to manage your actual physical components, part numbers and drawings of physical things, your architecture, all that stuff is going to be managed within the different tool sets. And so we want to choose tools that are able to interact with each other, share data between each other. And there are quite a few vendors now that are producing products that provide the glueware to actually link data between tools. So I can have a requirement management tool, have that same requirement in a SysML model, and there's tools now that link the two together. So if I'm in the SysML model and I want to author a requirement, it will actually call up the requirement management tool and allow me to author the requirement and use the requirement quality attributes of the tool to form a well-formed requirement. And then that same requirement statement exists both in the SysML model tool as well in the requirement management tool. Once we have the tools, then like this diagram shows, you got to come up with a relationship model and how you're going to maintain that. And there's different tool vendors have been doing studies on the benefits of this. And I know there's one, you can go to JAMA Connect site, and they have a thing about live traceability and how a lot of projects show more success when they have this degree of traceability established, maintained, and enforced within their tool set. Section 2.3 goes into defining interaction according to interface requirements. The phrase interface requirement refers to a specific form and template for a functional performance requirement. So when people say we're going to define functional performance requirements and then somewhere else we're going to define interface requirements, they're really creating problems, because if you really look at it, a majority of your functional requirements, just by definition, functional requirements, a function takes an input and turns it into an output. And so a lot of times you're going to have internal interface requirements as well as interface requirements to deal with external entities that are actually the prime function of your system. The interface requirement is the functional performance requirement, deals with the interaction of the system across some interface boundary, either internal to the system or with another system. As such, interface requirements should not be considered a separate type of requirement when organizing the set of design input requirements. Doing so, like I said, often leads to confusion and duplication of requirements. But they are a special consideration. So we have a separate section. Interface requirements may be included with functional performance requirements or with the fit operational requirements discussed previously. That could be in either one of the categories. All interface requirements have the same general form. And if the interaction is based on some condition, you'd have a condition statement to go with that. So condition, the system shall interact some function, verb, object pair, with another system as defined in some location. And a key part of interface requirements is that they include a pointer to where the actual interaction is defined. And this is important because that interaction has to be agreed to by both parties that are involved in the interaction. One of the big things that today's increasingly complex systems have is the amount of interactions between the parts, as well as the interactions with the external systems. And it can be quite complex. And so we need to identify all these interactions, both internal and external to our systems. And to a larger point, you can talk about the behavior of a system as a function of the interactions of its internal parts, as well as the interaction of the system with the external environment. When we talk about interfaces, there's an interface boundary and different types of interactions across that boundary. And then from a traceability standpoint, we can have a parent requirement that was allocated to maybe two other systems, and subsystem B has a child interface requirement. Subsystem C has a requirement. And so it turns out that in order to meet the parent requirement, subsystem B and C have to interact with each other. So from a traceability standpoint, we want traceability of the child interface requirements with their parent. We want to trace peer-to-peer, and we also have a trace to the common definition. That could be like in an ICD or some other document that includes the common definitions for how the entities are going to interact with each other. When you look at the interface of a system like here with the spacecraft, we have to look about interfaces across the life cycle. And there could be the many interactions with each group. So you can see that addressing just the interfaces could be a large percentage of requirements for the entity that we're defining requirements for. One thing that's interesting I talk about there's the interface requirements audit, where you take and talk about your system of interest interface requirements. You talk about the definition they point to. You talked about external system interaction definition, external system, and then external system interface requirements. And when you do this interface audit, you'll find like there's a problem in that my requirements pointing to definition 112, but the other system's pointing to a different definition. So if they're both pointing to different definitions, the chance of the interaction between the two is not going to work. In some cases, I have an interface requirement with one system, but the other system doesn't have a requirement to interface with me. So again, we have a problem. In some cases, we have where I have an interface requirement, but the definitions are TBD for both parties. And so this audit is really helpful, and it's surprising how much red you find when you go do that. There's an 1.5-hour presentation on the INCOSE RWG YouTube channel. And in there, you'll see that there's a talk on everything you want to know about interface afraid to ask that's based on what's in the needs and requirements manual. When we get into section 2.4, we're talking about attributes to develop and manage the design input requirements. There's a lot of different attributes that we can use, the rationale, trace the parent. There's a question to ask, what's the difference between a parent and a source? A parent is one source of a requirement. Because we do the lifecycle analysis and needs definition for each entity, our requirement could point to a need that we define through that process. It could point back to a goal or an objective. It could point to lifecycle concept. That's where we talk about the source. So where it originated in that case. But if you had a parent requirement that was allocated to your system of interest, then that system expects to see children requirements that address that allocated requirement. And so we're going to have both the trace to parent, trace to source. I talked about the allocation and budgeting part, and there's a whole bunch of other attributes that we can use to help better define and manage our requirements. There's like 40 some attributes. It'd be very difficult to include all these in a SysML model, but requirement management tools, it's fairly easy to include these different sets of attributes. Further explanation about attributes is included in section 15 of the Needs and Requirements Manual. And then section 2.5 gets into planning ahead for system verification. One way to improve the quality of our requirements, and also from a schedule budgeting standpoint, we need to go and look at, for every requirement, how we're going to verify that requirement, how we're going to validate that requirement. When I just use the term verify the requirement, validate the requirement, so that's making sure we have well-formed requirements. But we also have to talk about how we're going to verify the system meets the requirement. And so we talk about system verification. That's why I have the term system verification. A lot of people talk about requirement verification as if it was system verification. It's not. They're totally two different things. So we have to make sure that our requirements are verifiable so that the system can be proven to have met those requirements. So the best thing to do is address system verification when you are crafting your requirement. The guide writing requirement has that characteristic I said, verifiable for well-formed design input requirements. Verifiable means each requirement statement is structured and worded such that its realization by design and the resulting system of interest can be verified to have been met to the customer regulator's satisfaction with some level of confidence the level of requirement exists. A best practice to ensure design input requirements are verifiable is to do this planning. All this information should be defined concerning system verification for each requirement. And we talk about the method, the strategy, the success criteria, and the organization responsible for planning and execution of that verification activity. And so we have certain attributes that are defined that you can include that information in. In the past, when people talk about verification requirements, what they're really talking about were these attributes. And so rather than talk about verification requirements in the manual, we talk about these verification attributes. For needs, we also have validation attributes, just like this. Section 10 goes into a lot more detail concerning system verification, method, strategy, success criteria, and section 15 on the discussion of the use of the attributes. We're going to finalize our design input requirements. We have to record those, and this is where we get into the document-centric versus the data-centric again. We want the set of design input requirements to be recorded within an integrated data set in a form and media suitable for review and feedback from the stakeholders, as well as support traceability across the lifecycle and requirement verification validation activities, and also traceability between other tools. We assess completeness, consistency, and correctness. Those are key characteristics that we want of our requirements in sets of requirements. And assess feasibility and risk. Well-formed requirement statements have the characteristic C6 feasible, and sets requirements have characteristic C12 feasible. At IW, I gave several presentations on the Guide to Writing Requirements, Section 2, which was the characteristics of individual needs and requirements, and Section 3, which is characteristics of sets of needs and sets of requirements. And those presentations are available on the RWG YouTube channel as well. We had all these activities, so now we're here. We're going to baseline and manage our design input requirements. The details of the actual approval and baseline process are covered in section 14, needs, requirements, verification, validation, management. As part of the approval and baseline set of design input requirements, the team's going to need to complete design input requirements, verification, and validation activities defined in section 7. And again, requirements verification, how well they formed, requirement validation, do they communicate the intent of their source or need from which they were transformed. These activities are crucial in ensuring these characteristics. And then section 6.4 is an important thing about architecture levels, flow down, allocation, and budgeting. Unless the system of interest requires no further elaboration, as discussed in section 232 on levels. Once a set of design input requirements have been defined, verified, validated, baseline, the project team is going to flow those requirements down to subsystems and system elements at the next level, the physical architecture, via the activities of allocation and budgeting. Architecture definition, design input requirements definition that are concurrent activities that go together iteratively and recursively as the project team defines the levels of the architecture and then flows requirements down to the next level and then repeats. Requirements at one level are allocated budget to subsystems at the next level. And as this diagram shows, their inputs then into the lifecycle concept and needs definition process. In theory, for every part of the architecture, you're going to have lifecycle concepts and needs defined, which will then be transformed into the set of design input requirements for that entity. And this repeats until I need no further elaboration and I'm ready to actually implement that design input requirements into design. And then we've crossed the line between design input and design output. All these requirements, like I say, are inputs into the lifecycle concept needs and requirements definition. And the process then repeats till we make the buy, build, code, reuse decision. Section 6.4.2 talks about product breakdown structure and document tree. So like from a project management perspective, the physical architecture be mapped to a product breakdown structure, which is similar to a work breakdown structure. Every one of your entities are going to be part of that product breakdown structure. Each entity is going to have a budget, schedule, concepts for development, procurement, and they're going to have sets of engineering artifacts. And so it forms a document tree, what some people historically have called. In a data-centric world, all these sets of information we would like to be able to maintain within our tools and to be able to link those together through traceability. Completely describe a system of interest, lifecycle concept needs and requirements, sets, and it said sets for each entity within the product breakdown structure are needed. So you have this hierarchical family of artifacts, like I said, in the document tree. And then allocation is some people call the flow down of requirements. It's a process by which the design input requirements defined for entity at one level of the physical architecture are assigned to flow down to the entities at the next lower level of the architecture that have a role in implementation of that allocated parent requirement. Based on analysis of the design input requirements and the functions of the system whose requirements are being allocated, the architecture definition process decomposes the system into subsystem system elements, resulting in the next level of physical architecture. And for each subsystem or subsystem element that has the role in meeting the allocated parent requirement, the requirement will be allocated to those subsystems or system elements. Allocation, again, is linking a requirement at one level to part of the architecture at the next level. In theory, when you're doing allocation, the next lower level has no requirements defined yet. So these are inputs that are going to be used when we go through all the lifecycle concept analysis, maturation, needs definition, and then transforming those into design input requirements. The allocated requirements, like I said, are the inputs, and then the resulting set of needs are then transforming the design input requirements for each of those elements. And the allocated requirements referred to then as parents to the resulting child requirements derived to meet the intent of the allocated parent. And I know there's a question about derivation. Actually, when you are developing requirements at the next lower level, there's decomposition and derivation and there's elaboration. You have to look at all three of those different techniques when we're talking about defining lower level requirements. Are we deriving a requirement? Are we just further decomposing a parent function into sub-functions, say, or are we just providing more elaboration, more detail at the next lower level? Parent is allocated to multiple lower level entities. There's often an interaction interface between those entities. Here's an example of a medical diagnostic system. And so I have diagnostic system requirements. I have biological samples or inputs, outputs to that system, then are reports provided to the doctors, nurses, medical professionals, the patients. But the diagnostic system requirements are going to be allocated to different parts of the architecture. They may have an instrument, you have what they call an assay, which consists of a sample, a cartridge, maybe reagents, and then we have software requirements. that could have the GUI requirements for controlling the instrument, processing the data, and then how to output data, either display or in reports. And so all these are flowing down. Some of these, there's going to be an interaction. So the total time to produce a report from the time we take a sample, put it into a cartridge, put it into the instrument, that whole total time is shared between all these entities. So from a diagnostic system, we could have total time for producing a result, but we're going to have to allocate that to each piece of the architecture, and each one's going to have a role in that. And then part of the system engineering is to manage that allocation. You can use an allocation matrix to start with. We take each of our requirements and we look at the architecture and we put an X where we think each of those architectural elements have some kind of role in meeting that requirement. And then if your system of interest is like instrument subsystem 2, you would look through this matrix, and wherever there's an X, you know you've been allocated that requirement. So then you know you're going to have to develop child requirements in response to that. But then you also have to do an assessment. In doing that, do you have to interact with one of the other architectural elements? And if so, then you also have to assess what that interaction is and include interface requirements with that other part entity. So once the parent requirements have been allocated, they become constraints for each of the receiving entities, and the project teams that receive those allocated requirement will address what that means to them, what is their specific role they play in implementation of the intent of the allocated parent requirements, and then the roles are first going to be communicated within their needs and then transformed into the design input requirements. And the role must take into consideration, like I said, the role of other subsystem system elements that were allocated the same parent requirement, because it could mean that you have to interact with those other entities. And so then we have interfaces. And because one parent requirement is allocated to multiple entities, that whole dependency thing is important. And so when I talk about traceability, peer-to-peer dependencies, we want to capture that. And each child requirement for each of the receiving entities contribute to the realization of the allocated parent requirement. It's going to be common to have functional performance requirements allocated to both hardware and software. Now we have the concept of embedded software, different from a standalone software application. Now the software can't work in a world of its own. It has to work closely with the hardware components that it has an interaction with. So each entity project team is going to have to determine how each entity interacts. And like I said, this is a new concept for some software folks that they actually are dependent on the hardware. In a lot of cases, the hardware actually enabling systems for that software. And one thing that when we're defining child requirements, you do not just copy and paste the parent requirement and change the noun. The parent requirement says the system shall do X, and then someone copies that and says the subsystem shall do X. That is not a proper child requirement. Someone mentioned models earlier. That's one place where I think, the system modeling really has a strength when it comes to allocation, budgeting, managing dependencies and interactions. Much easier when we're using SysML models, the various different kinds of models, and all those dependency interactions can be discovered and managed within the models, helping to ensure consistency of the requirements within the set, as well as consistency with the requirements that have a dependency with the requirement sets of other subsystem elements. Budgeting of performance, resource, and quality is a key thing. Allocation involves more than just flowing down requirements from one level to the other. There's two types of allocation: assignment of responsibility. So the receiving entity has some role in meeting the intent of an allocated parent requirements. However, there's also allocation of quantities, such as utilization, performance, quality, or some physical attribute. It could include mass, volume. Just like the example I gave the medical device, the time to produce the output, the report, that was allocated. And so if the parent requirement was you got to put out a report within 5 minutes of the sample being inserted, then how much time is taken into processing the sample inside the instrument, how much time is taken the instrument getting the data, how much time does the software have to analyze the data, how much time does the software have to produce the report. Someone has to go and divide that 5 minutes up amongst each of those entities. And so the budgets need to be managed and controlled at the system level. And this can result in some lower level entities to be suboptimal in order to optimize the integrated system. And this is hard for some people to think, especially if we're in a siloed organization. People tend to want to optimize their subsystems of the system elements. In reality, what we're trying to do is optimize the performance of the integrated system. So in some cases, the lower level entities may be suboptimal in order to do optimization of the parent. And a data-centric practice, SE budgets are managed and controlled within the model of the system. And a critical concept associated budgeting is the budgeted quantities resulting requirements have a dependency. Change in one will result in the need to change another. And so we have the parent is allocated to the children, and you can look at that as an equation. When you're doing this, we have to balance the equation. So we can't change one of the variables on the right without looking at the change of any of the other variables, because we have to keep the left parent in balance. So again, this equation concept really helps be implemented within models. Another part of budget management is margins and reserves. Budgets are established as limits within a quantity that's being managed. There can be uncertainty. And this is really true when we're talking about developing new products, using new technologies. And some brilliant scientists may say you could get a performance of 15, but when you consider everything, maybe the best you're ever going to get right now is get the state of the art is 10. So we have to realize that, and then we can manage that uncertainty using margins and reserves. We'll go into a little bit of detail on that in the manual. And if you don't manage your margins and reserves, you're adding risk to your project of not being in performance. The major problem is a lot of engineers aren't really familiar with the concept of margins and reserves. And we have to think about it during development, the technical margins, just in building that new system, the new technology. We also have to consider operational margins, operational capability. You know, the first lunar lander, when it landed on the surface of the moon, when they actually touched down, there was fumes left in the tank. So ideally, you want to think that the people allowed enough volume of fuel to allow some uncertainties so that they were able to safely land. We can think about that during operations. And then just the management reserve issue, all the uncertainties that happen as we're developing products, the unknowns may cause us to have to do additional rework. That's going to hit our budget and our schedule. So we need to include those management reserves as well. The size of the margins are based on the risk associated with the projects. Early established of adequate margins and reserves and the effective management of them through the product's lifecycle play a critical role in the ability of the project to deliver a winning system. Failing to define margins places the project at risk of cost overruns and schedule slips. When defining the values within design input requirements, it's critical these values take into consideration of margins and reserves defined being managed by the project. So even though the brilliant scientist said 15, you have to consider what's realistic. And if this state of the art, only 12 is realistic, you should write the requirement for the 12, not that theoretical 15. Use of traceability and allocation together helps us manage our project better. When we combine those two, there's a lot of defects that we can find as we're going from one level to the other. Answering a key set of questions will help us have a more complete, consistent, and correct set of requirements. So we can assess which requirements at one level were never allocated. That means that if they weren't allocated, then the lower level systems won't have child to meet those. So those requirements will not be fulfilled. Requirements that are not allocated correctly, they may have been allocated, but not to the proper lower level system elements. Parent requirements that have no child requirements. Allocation took place, but no one wrote a child requirement to address that parent requirement. Needs that have no implementing design input requirements. Orphan needs that don't trace to a source. Traceability is not just the requirements. We have traceability in our needs as well. Orphan requirements that don't trace to a need parent or source. Need sources requirements incorrect or missing implementing child requirements. Requirements with an incorrect parent or source. Someone wrote a requirement, but they trace it to the wrong parent. That could be a problem. One of the challenges I find with requirement management tools is show me a report that shows all child requirements that trace to a parent that was not allocated to that lower level entity where the child is. And most tool vendors cannot produce a report because they really don't even understand the concept of allocation very well. Sets of child requirements not necessary and sufficient to implement the parent requirement need to source of which it is transformed. There may be child requirements, but we don't have a necessary and sufficient set that will result in the parent being met. All of these common issues are discussed in detail in section 14 of the manual. Coming to a close, section 6.5, the summary design input requirements definition. The focus of the design input requirements definition is defined well-formed sets of design input requirements for the integrated system, as well as each subsystem and system element within the physical architecture. So again, we have multiple sets that we're defining for the integrated system. These sets of design input requirements represent the allocated baseline to which the design definition process will implement. And well-formed refers to the quality of sets of design input requirements in terms of content, as well as the structure as defined in the COSE Guide to Writing Requirements. And the goal is to have well-formed sets of design input requirements that clearly communicate the intent of the needs to the users of the requirements, and ensure the sets of design input requirements have characteristics of well-formed design input requirements as defined in the Guide to Writing Requirements is necessary to ensure high-quality requirements that will not be as volatile as many organizations currently experience. One of the big complaints that people have about requirements that they receive is they are poorly formed. They don't have the characteristics in the Guide to Writing Requirements. So there's a lot of churn and change in those requirements because the upfront analysis wasn't done, and the resulting set of requirements may be incomplete, inconsistent, not feasible. One big question is, how do we know when our requirements are done enough to proceed with the design? There's always a trade-off between better and good enough. In our definition, good enough is the point where cost and potential changes is less than the effort needed to define every requirement. And there's really no simple indicator. The decision's knowledge-driven, not schedule-driven. Baselining a poorly formed set of requirements often results in accumulation of technical debt that would be more costly in terms of both schedule and budget, rather than spending the time and effort that result in well-formed sets of requirements as discussed in the guide and the manual. Section 7 focuses on design input requirements, verification, validation. It goes to a lot of details, checklist that you can go through as part of each of these activities. You're going to go through these activities as part of the baselining of your requirements. And so we're asking key questions about, do they have the right characteristics individually and as sets? Have we defined attributes for each requirement? Do we have the traceability established? Do they clearly communicate the intent of the integrated set of needs for which they are transformed? Requirements verification, validation.
I have a quick question, Lou. Like you said early on in the presentation, that we do so much more than just write requirements. I remember in telecom, we would create like SDL diagrams that would show, like you mentioned, embedded systems and all the real-time activities that are concurrently going on. How do you actually link all that in with your requirements? What does it actually look like? Like you mentioned Java Connect. I mean, would you just do it all within a tool like Java Connect? Is that how it would work? Or?
You'd record the key information within the tool. That way you can establish traceability between those data items.
Think of them as have a traditional tool to track your requirements, and they're kind of like linked, like hyperlinked within your model.
Okay.
So if you have a particular element of the model, it has associated attributes that are like wind up being requirements.
You're linking requirements to certain
elements.
aspects.
Yeah, so if you have an element in the model, it's linked to that element.
Okay.
And that's what the
requirements
connection
linked
does.
to an element.
Yeah.
Okay.
So one of the problems that we have is that some of the legacy tools were really just requirement management only tools. Today's modern tools are so much more. They're really data and information management tools, and requirements and needs and lifecycle concepts, use cases, user stories, ops scenarios, needs, goals, and objectives. All that are data items that need to be documented and managed in a form that you can establish traceability between those. So even though, tools like Java Connect exist and they call them requirement management tools, they really are so much more than that. They're data information management tools.
Okay, thanks, Lou.
I have a follow-up question. So Lou, it's quite an impressive and compelling body of knowledge that the requirements working group has put together in the form of these manuals and guides. And if you think about companies, they have their own culture, they have their own language, they have their own sort of SOPs, way of doing stuff. What would your advice be in terms of taking what the requirements working group has done and all these manuals and guides and applying them to their own culture, SOPs, organization, etc.?
Very good question. We're already providing methods and activities that result in knowledge that is important to understand, even though the terminology that we're using in the manual may not be the same in an organization. A rose is a rose no matter what the name is. And so they need to go and look at what's the outcome of these activities, tailor that to their particular domain. And some of the working groups, like the System Security Engineering Working Group or the System of Systems Working Group, they're planning to develop in a guide that's kind of a Rosetta Stone, if you will, between the vocabulary used within the manual and vocabulary used within their disciplines. So organizations can do the same thing. They have to say, what are some of our problems? What are some of our pain points? Or some activities that are defined in the manual that we could include within our processes and to make it work. What's in our documents isn't really intended to be prescriptive that you have to follow every step. It's just saying that every step has reason and purpose. There's knowledge to be gained, and you have to decide whether or not you need that knowledge or not, what the consequences or risk of not addressing that knowledge, not doing that upfront work, and so on.
And a perfect example of that is needs. I think most companies, they don't go through that needs exercise. They jump right to requirements. Yeah, I think that's a really good example.
One of the problems that we have is the customer-supplier relationships. If you're a developer and the customer hands you a set of requirements, as has been done in the past in a contract, then your focus is on meeting those requirements. You don't know what work and analysis the customer did to produce those requirements. Sadly, a lot of those sets of requirements are really poorly formed, which is putting the whole project at risk. So customers need to understand that they need to do this upfront work in producing a set of requirements that they're going to put under contract. And they should make available some of that analysis to the suppliers. Hopefully, if they started using system models, wouldn't it be nice if they could hand those models over to developers and developers continue to use? I don't know if that's ever going to happen, but it could. Or if they have a set of needs that they've developed the customer, why not make that available to the developer? And in some cases, it makes more sense if you contracted the set of needs, let the developer define the set of design input requirements and require part of the deliverables allocation traceability matrices to make sure that all the needs are done, and then get customer approval on that sets of requirements, but have the developer define those and answer the question, what does the system need to do to meet the needs? And I've seen in the DoD, they have sometimes that they call a statement of objectives. And those objectives really are an integrated set of needs. They're just communicated differently. And I've seen some cases where DoD put out a contract and said, here's my needs, say, for communication satellite. And the satellite people said, well, we have one on orbit that will meet all your needs. And so the DoD didn't have to pay for a new satellite. They could just buy communication as a service from an existing satellite that met all their needs.
Thank you very much, Lou. As you can see, we're willing to talk about this all night long. So thank you.